In this video, we're going to be reviewing binary trees and binary search trees. So, what is a complete binary tree? A complete binary tree is when you have each node, and each node is going to have either 0 children or 1 child. So, it can also be stored in an array. So that's going to look like this. Your index values are going to be these. So, or actually, I'm going to put that down there. So here are your values. You're going to have like 0, 1, 2, 3, 4, 5, 6. You can store your tree into this array representation: 4, 12, 2, 6, 10, 14, because remember, a tree is really a bunch of pointers and references. Pointers and references. So this would be the representation of a tree like this: 8, 4, 12, 2, 6. Some important formulas. When you have, here you have zero-based indexing. Zero-based indexing for these formulas, you're going to have for a node at index I, your left child is equal to 2i plus 1. Your right child is equal to 2i plus 2. And your parent is equal to index minus 1 divided by 2. Now, this is for complete binary trees. Let's move on to BST insert. This is a good topic. So, what you need to know is that insertion is recursive. So the rules are that if your value that you're considering is less than your current, you are gonna go left. If the value you're considering is greater than your current, then you're gonna go right. So remember that in a binary search tree, everything you're gonna have, for any subtree, you're gonna have nodes in your tree, right? But you can, for any one of your subtrees that you consider of a node, it's always going to follow this rule. You can just split it up into 2 sides, your left side and your right side. So it's going to point here to 2 trees, right? So on the left side, it's all going to be values that are lesser, and then on the right side, it's all going to be values that are greater. And this will work in each of these trees, subtrees, there's a node, and then you can do this again. So that's why you can consider that to be a binary search tree if that's true. So for example, if you have a node that is like this, or you have a tree that's like this: 50, 30, 70, and 60, what you can see is what we want to do is we want to insert 65. But we want to follow the rules of this BST. So how do we insert 65, and where do we know where to insert it at? Where it would fit here. So first, you're going to compare. So you know that 65 is greater than 50. So that means you go right. And I'm actually going to do this with colors so you can see where it goes. So you're going to go right, not to left. Now here you can see that 65 is going to be less than 70. So you're going to go left. 65 is less than 70. Go left. So you're going to go this way. And now here you're going to insert here. Insert here. So you're going to have 65 on this side. Now that's your answer. So let's move on to BST search. And we want to talk about the time complexity. For time complexity. So in your worst case, which is going to be when you have a skewed tree. And a skewed tree, it basically means that it's like this. So you're going to have values like this is like 4, 3, 2, 1. That's what it means by skewed. It's skewed in one direction. And then in your best case, or in your good case, is when you have a balanced tree. Like, let's look like this, for example. This is going to be a time complexity of O of n, big O of n. It's going to be a time of O log n. So when you have that's for BST. This is if balanced. Now, don't get confused with a binary search array. It's going to be O log of n. Those are different. So now let's talk about BST delete. For BST delete, you're going to have 3 cases. So for case 1, this is when you are going to be deleting a leaf. So when you have this, you just remove that leaf. You just remove it. Now for case 2, you're going to have a case where you delete a node with 1 child. So that's like you have so here's like you have a node and you want to delete this one by. But then here you have a node and it has like 1 child. So you want to delete this one, right? By. So this is tricky. What you're going to do is replace that node with either so 1, okay, I'm gonna say, wait, no, I'm just gonna say in order successor. So that's gonna be the smallest in right subtree or the in order predecessor, which is going to be the largest in your left subtree. And most of your algorithms are going to use this one. Algorithms. So you're going to take the smallest in the right subtree. So you're here, you're like looking at the smallest, but here you have nothing, obviously. But here, in order predecessor, largest in the left subtree, we have to take the largest in the left subtree because there's nothing in the right. This is going to be null for our example here. So now let's do case 3. Case 3 is when you are asked to delete a node with 2 children. So let's like look at this tree again. And we want to delete this node. So what's going to happen here is let's do an example with like actual numbers. So you have 50, 30, and you also have 70. And you have 60 here. So we want to delete 50 by. So we're gonna replace 50 with 60. So what's gonna happen is this is gonna look like, I guess, just right here, you're gonna have 60 and you're gonna have 30 and 70. So that removes the original 60 node. Now we're gonna talk about when you have like written parts on your exam in data structures or AP CSA, like you have a FRQ, you have a recursive height code that you need to know. You're gonna have to replicate this based off like which scenario that they give you. They usually give you something where you have like methods and stuff and like restrictions and stuff on your formula sheet, but like, or your cheat sheet is like called your reference sheet, but this is, yeah, like height is going to be computed recursively, so you're going to write int height node root if the root is equal to null, return -1. That's your edge definition. And then you can declare int left height is equal to height root dot left. And you also have int right height is equal to height root dot right. And then you have return 1 plus math dot max left height right height and close. You need to remember your base case returns -1 if you're counting edges. Or 0 if counting nodes is what you could replace this with. Now let's write the code for tree size. Tree size. So let's say it's another recursive tree size. Okay. So this is like when you have int size node root. If the root is equal to null, you're gonna return 0. And you have return 1 plus size root dot left plus size root dot right, and this. Now your time complexity for this code is going to be O of n. Now let's write the code for counting leaves. Counting leaves. So to count leaves, you have int count leaves node root, and it's going to be if root is equal to null, you're going to return 0, and if the root dot left is equal to null and root dot right is equal to null, you're going to return 1. Now you have return count leaves root dot left, it's lowercase l, left, plus count leaves root dot right. Now let's also talk about the skill of checking if your tree is balanced. So for these types of things, you're going to have to look at your height balanced definition. So that's when you're going to take the height of the left subtree minus the height of the right subtree. So in order for it to be balanced, this value has to be less than 1. Now let's talk about the lowest common ancestors with BST. So you're gonna have this when we already know that like If you have your value is less than your root, you go left. If your value is greater than your root, you go right, right? So now if both vals are less than the root, yeah, you still go left. And if both vals greater than the root, you go right. For example, let's consider this question. Find the LCA of 30 and 60. So you're gonna have this tree like this. 30, 70, 60. Here we know that 30 is less than 50. And also we know that 60 is going to be greater than 50. So that means that LCA has to equal to 50, the lowest common ancestor. So let's also talk about tree traversal complexity. Tree traversal complexity. So when you have all of your DFS traversals, they're all going to be in O of n time. And your space complexity, it's always going to be space. It's going to be O of h because of the recursion stack. I don't like being like this, worst case, again, we already talked about those. Worst case is O of n if skewed, and balance is O log of n. Let's talk about reconstructing a tree. Reconstructing a tree. So this is if you're given the pre-order plus in order, and you want to reconstruct that tree, reconstruct the tree. The pre-order first element is equal to the root. So you already know what the root is. So then you can figure out that, and then you're going to use this in order, and you're going to split at the root based off of what you know that in order gives. And then from this, you're going to recursively build subtrees. Now let's talk about a heap versus a BST. These are different data structures. When you have a heap, it's going to be a complete tree. Also, in this case, your parent is going to be greater than or equal to your children. And that's going to be when you have a max heap. And then you also have no ordering between your siblings. However, in a BST, this is when your left is less than your root is less than your right. So also it's not necessarily complete. So they're not the same thing. Yeah, so I'm going to go back to the big O's. Where did we put the big O's? Yeah, here. So this is for your worst case, your good case, binary search array, all DFS, and the space complexity. So let's go back to here. So when you have let's compare for operations. When you have search, insert, and delete. So when you have a balanced BST, binary search tree, versus a skewed BST. So these are all going to be O log of n, and these are all going to be O of n. Write that like that if you want to. Again, remember the in order of a BST is not sorted. So also pre-order does not mean that it's sorted. Remember that perfect, the definition of perfect, which I've gone over in other videos, is when you have full plus complete plus a same leaf level. It has to all be on the same leaf level. And also remember, height and depth are going to be different. Depth is you're counting your edges. Height, you're counting the longest path. And also just keep in mind the index formulas that we went over. The index formulas here. So yeah, I'll actually box this whole thing.